Hello people, welcome back to the corgi64 project where we're building a simulated computer from scratch. Where we last left off, we created we added basic arithmetic opcodes to our system. The add, subtract, multiply, divide, and mod operators, and we also separated our code out into a cpu.h file. That allowed us to have a more compact main file. So this time what we're going to do is we're going to take a look at adding a couple more of these register functions, and maybe if we have time to get a CPU loop up and running. So let's go and take a look at some of these functions. So what the first thing what we want to look at is this set an immediate value for A. So we're going to set immediate value for A, and probably do for B and C as well. So let's go over to our cpu.h. Let's scroll up. Let's see. All right, after here, we'll say we have our register opcodes. May not need that, but it's going to be static void. In fact, what we may want to do here is static is kind of an overloaded term. It means different things in different contexts. What we may want to do is define static, define local as static. I believe that's the order that it should go in. So then what we could do is we could say, let's take all of this here and let's do a find everywhere there's static in the selection. Oh, actually what we want to do is we want to do a selection, find static, and replace it with local. So that way it makes a little bit more sense. There we go. Replace it with local. There we go. That might make a little bit more sense that we want this to be a local function. Now let's see. What we're going to do here is we're going to create a new function, a local void. Let's see, what do we want to call this? We're going to call it SIA for setting register A to immediate value. So SIA, and we're going to give it a pointer to the CPU. And the way that this will work is we set A to an immediate value, which will be in our let's see, it will actually be in our CPU memory with the value of our, let's see, what do we've got? It's going to be our program counter. So the way that this works is we're going to be reading our instructions. Oh, actually, that's another thing that we're gonna have to think about. So this actually won't be exactly the case. Okay, the other thing that we're gonna have to think about is how we're going to read our instructions in memory. So we have this memory, which is just a sequence of bytes, and there's right now with our CPU design we have two different possibilities. We'll either have a single byte where it's just an instruction that says what to do, or in the single byte instruction maybe something like add. And add adds the values from registers A and B together and stores the result in register A. Now the interesting thing about this store immediate value in register A is that we have to get a value from somewhere, and we get it from our program. And the way that that works is we have to read that value of our program in memory. So the way that we're going to do that is, well, here's the problem, is the single byte instructions are just a single byte, and that's fine because our memory is in bytes. But addresses and immediate values will be a 64-bit value. So how are we going to get 64-bit value from a only single byte memory array? Well, we have to read multiple bytes at the same time. And the thing is, some computers are, well, most of them are little endian and some of them are big endian. And what the endianness of a computer, or the endianness of a system means, is the order that the bytes show up. So when we write a number, say 1, 2, 3, 4, 5, we put the most significant value first and the least significant value last. So the 5 is the ones place, 4 is tens, 3 is the hundredths place, 2 is the thousandths place, and 1 is the 10,000ths place. Well, there are two different ways of writing numbers. We could write numbers that way, or we could write it the other way, where this is where the first number is actually the least value. This is still the ones place, tens, hundreds, thousands, and 10,000s. And the different ways of writing have different they have different pros and cons to them. It turns out that some are easier for the computer to do math with than others. And we don't want to have to worry about that. We don't want to have to worry about whether our system is big endian or little endian, whether it stores the largest, most significant bit in the left or rightmost value. What we want to do is we just want, if we had to worry about that, then we'd have to worry about reading our memory in the right order. So in order to not have to worry about that, what we're going to do is we're actually going to create a struct called an instruction, and what we're going to do with it is, this is actually, oh yeah, we're in C++, so we don't have to worry about doing a type def. So we're going to create an instruction, and the instruction is going to have an opcode, which is just a byte, and then it will have a I64, which will be, this could be either an address or an immediate value. So we're just going to call this value. And what we're going to do is when we read from our memory, we're actually not going to read a single byte. We're actually going to read an instruction. And the instruction will contain an opcode in the front and then a value in the back. Now, for the instructions that don't, for the instructions that only have an opcode and only 1 byte, we can just ignore this value, because this will actually be some other part in memory that we won't care about, and we'll just look at the opcode. But for something that does have an opcode and a value, we're going to read both the opcode and the value. And this will be kind of like a way of decoding the instruction. So when we get to the part of the CPU where we do the decoding, we'll actually just read the memory using this instruction, and we'll go into how to do that. So what we're also going to need is a register in our CPU, which will be the immediate instruction register, and we'll call it instruction and instr, instruction register. And this will allow us to, when we read it, we will read the instruction into the CPU, and it will have this register that will hold the instruction for us, and then we can actually do whatever we want with this instruction when we go to execute it. So when we go over here, or actually down here to our register opcodes, what we're going to do is we're going to actually look at the instruction register, and we're going to access the value. So we're going to set register A, which is an I64 to the instruction value. So that is what we're going to, and that is how our opcode is going to work. We can actually take this and copy it. And how many more of these do we have? Oh, we have to do this for B and C. So this will be store or set an immediate value for B, and we're going to set an immediate value for C, and then we'll set this to B and C. Okay, so that is how we will set up our instruction immediate values. We can do this by, now we want to add some tests for these things. So let's go down over here in our test.cpp file and write void test SIA with a CPU pointer to our CPU, and we actually need to create an instruction. So let's do instruction equals the let's see, actually, how do we want to do this? We'll just do instruction dot opcode equals actually, we're not going to test out the opcode for this word or the opcode value for this. We're actually just going to test the setting the value. So we'll set a value of 3, and then we will say let's see, we need to have a SIA, so we'll do a SIA with our CPU, and at the end we want to assert that the A register is 3. And then we'll also do a printf where register A is some number. We'll say int 64t CA. There we go. So that should be a good test to see if that works. And let's do the other two where we set B and C, and then we'll say, okay, we're going to have register B and register C here, and this is register B, this is register C. So here we have, let's see, register B and C. Now, if I did this correctly, we should be able to compile or actually build tests. Nope, looks like we have some errors. We're missing some semicolons. So let's take a look at tests line 46. We're doing something incorrectly here. Oh, yeah, we can't. In C, we cannot use the hyphen as we can't use a hyphen in our what do we call our names. You can do it in Lisp, but you can't do it in C or many of the other C-based languages. So let's do tests, and okay, all of our tests pass, but that's not saying too much because we want to test, this is testing arithmetic. This will test immediate values. We're going to do test SIA, test SIB, test SIC. Now if we build this and run the test, oh, looks like we have some sort of error. Register A is 3. Did we, let's see, Oh, yep, it looks like some of these things, SIA, we're doing SIA, but this needs to be SIB, and this needs to be SIC. So now we can build this again and run it, and it looks like all of our tests have passed. Register A is 3, B is 3, and register C is 3. If we want, we could actually pick some different numbers for these. We could say, okay, register B should be 4, and register C should be 5. Shouldn't make a difference. Now we have register A is 3, B is 4, and register C is 5. So that's very good. Let's take this, and now that we can load values into our registers, let's see if we can get our main loop running. So we'll go back to our cpu.h. Oh, and we also need to add these opcodes to our op table. So let's go to our design. This will be 01, 02, 03 for SIA, SIB, and SIC. So 01 will be SIA. Whoops. 2 will be SIB. SIC for 03. So now we've added those to our opcode table, which is great. Now what we can do is, let's see, what else do we need to do for this? We have our opcode table set up. We've got these set up. Let's see if we can set up our main loop for our system. Now the thing here is we don't have a flag for whether our system is running or not. If you notice in our CPU design, we actually don't have, I don't think we have, a halt instruction. No, we do not. So what's going to happen is, for right now, we may insert a halt instruction later on. Right now, what we're going to do is when we run the computer, we're just going to run it in an infinite loop, and we're going to, let's see, we need to, okay, the way the CPU works is it essentially does three major things. Actual CPU, okay, the three major things that a CPU does is that it fetches an instruction, it decodes that instruction, and then it executes that instruction. Those are the three major things that a CPU does in an infinite loop. Now it turns out that it's a little bit more complicated than that in real hardware, because in real hardware you have to worry about actual electrons and other things that are going around, and pipelining, and just a lot of things that we're not going to take a look at here because we don't have to deal with hardware. That's the beauty of having to deal with software. So what we're going to do is we're going to write these things down: fetch, decode, and execute. And the way that we're going to fetch an instruction is we're going to say, okay, our C instruction register is going to be where our memory is at. Actually, let's see, we're gonna actually coerce this into being an instruction, and we're gonna have C memory at location program counter. And remember, our program counter, let's see, our program counter, oh yeah, is an i64, that's fine. So hopefully what this means is that we will, starting at some byte that our program counter points at, we're going to read a full instruction, which is 9 bytes, into this instruction register. Now, simply by doing that, we've already decoded our memory into an opcode and a value. So it turns out that we've automatically done our decode step. So we're just going to say fetch and decode. So that has simplified things immensely. And then the way that we execute that instruction is we have the op table, and we will look at the opcode that's in our instruction and execute it. So what will happen is this instruction opcode, it actually gives us a number, right? Because remember, our opcode is just a byte, which is a number. In fact, what we probably want to do is convert that into, let's see. Well, it may work. We'll see if it works or not. This is just a number, and we're going to look at that number inside the op table. So whatever that is, let's say it's the number is 1, so we'll get this function from our op table, and then by having the parentheses on there, we actually execute that op table or that opcode, and we need to give it our CPU, of course, and that is how things will work. We'll fetch and decode, and then we'll execute the instruction. Now, what will happen here is there is eventually, if we have, say a little bit of memory, we'll have different opcodes in our system, and eventually we'll reach kind of the end of our system. Oh yeah, the other thing that we have to worry about is we need, after we fetch our opcode, what we need to do is we need to actually move along to our next opcode. So what we want to do here is we need to, now there's ways that we could write this a little bit more compact than what we've got, but this will be incrementing the program counter. So we'll fetch and decode, then we'll increment our program counter. In fact, let's just put this above since we've got our comments above for everything else. We'll fetch and decode, we'll increment our program counter, and then we'll execute our opcode. All right, so that should be everything that we need to run our system. Now, the thing is what we want to do is maybe we should have a halt instruction, because we don't want to go off into memory that we don't have control over. So let's go to our CPU design, and at the end here, after no op, we're going to have x2e, which will be a halt instruction. The halt operation, and what halt is going to do, we'll have to create a halt. Let's see, so what we're going to do for right now, we may actually keep it this way, but we're going to have a Boolean running flag, and we're going to actually, for all of this, so okay, we're going to have our Boolean running flag, and then when we run our CPU, we're actually going to set running C running to true, and then if we have a halt, we need to turn that running to false. We also need to say while the CPU is running. So let's go over here. Let's set, after our no op, we'll have a local function void halt CPU C, and what we're going to do is we're going to set running equal to false. Then we should probably also write a test for that. We actually don't have a test for the no op, but the no op does nothing, so there's not really too much of a need to test that one. But we'll have a void test halt CPU C, and we'll set C running equal to true, And then what we'll do is we will halt the CPU. And then we will check that running equals false. And we'll print running is, and we'll just print that out as an integer. We'll do C running, and hopefully that will work. Let's go down here and actually run that test. We'll have miscellaneous tests, and we'll do test halt with our CPU. Now let's try building. So we'll do a build. Looks like we have something a little bit wrong. CPU 94, we cannot convert from byte to instruction on the typecast. Oh, and that's because we're in C++, I believe. So we're going to have to do a different type of cast. No constructor could take the source type constructor overload 94. So let's go to 94 on our CPU. Line 94. Okay, so we can't just do a type coercion. We need to do a, let's see, a reinterpret cast instruction, and I think that's how we do it. Normally they tell you not to do these reinterpret casts, and in general that's true. You don't really want to do reinterpret casts all the time, but we're building a CPU. It's kind of a special thing. So hopefully I did that correctly. I may need a standard on that. So let's do build test. Reinterpret cast. Cannot convert from byte to instruction. Is that not true? Actually, what we may do here, do I need standard? Let's do a build, reinterpret cast illegal. Oh yeah, so I don't need that. So I'm pretty sure I need a reinterpret cast to an instruction. Actually, what I'm thinking about, and I've been thinking about this for a little while, is maybe just converting this completely to C. But we're doing a C memory. Oh, you know what? This is getting us the. This is actually getting us the actual single number at our memory. So we're, instead of getting a pointer to a single place, we're actually getting the value of a byte. So we don't want that. What we want is we want the pointer, or we want the memory location. So perhaps what we'll do here then is we'll do mem. Does that? Let's see. So mem plus. So mem is a pointer, and we're just adding on that number of bytes. Let's see if actually. Let's see if that. Let's see if we can get away with doing a cast to instruction. Whoops. Let's see if we can get away with doing that. Typecast cannot convert from byte pointer to instruction. Oh, instruction needs to be, that probably needs to be a pointer to memory. So let's make this a pointer to instruction. That also means that in the resetting the CPU, we need to say that if if C instruction equals null, then we need to reserve some memory for it. So we'll get the instruction equals instruction malloc size of instruction. So that will reset our CPU, and let's see. And hopefully in our test we actually reset the CPU. Good, very good. So we're going to reset the CPU. We're going to, if the instruction is null, we're going to make it a real one. Let's see, this should be a pointer. We'll do a build. Whoa, okay, so let's see. Left of dot value must have class struct union. Ah, yes, so we're making a little bit of progress, kind of. So CPU 49, what we're going to do is we're going to take a look at this, and this actually needs to be, since this is not an instruction but actually a pointer to an instruction, we can't save value like that anymore. We have to actually use the arrow operator, and that will give us the value that way. Then also in our tests, I think, yes, in our test we're going to have to do the same thing when we get our value. Now let's go back to the CPU. Let's see if we can do a build. Okay, so now type is instruction pointer. Let's see, it looks like we missed one more. So in 101, yes, we missed one more. We need to do this, and it looks like we may be able to do that. Okay, so let's do a bin test. Looks like we missed something. So, and where was this? So we stopped at 3 mod 4. So let's go to our test. Let's see, so we had, so this is at our instruction. So let's take a look at this. So we're missing something here. Oh, that's probably because, let's see, we reset, and we need to set the, well, let's see, if we reset our, if we reset this, this should actually malloc for us. Oh, another thing that we should do is our destruction. Do we write a free yet? We'll have to do that at some point in time. We'll get around to that later. So right now what we're going to do is we're going to check and make sure that this actually sets up our instruction. Printf allocating memory for instruction register. We'll see if this actually happens. If it doesn't happen, then what we're going to do is fix it. So it looks like we never allocated memory for our instruction register. So what we'll have to do is we need to, when we create a new CPU, that's right, so don't we have a new CPU function? Actually, it looks like we don't. So we use the reset instead, so we create a CPU and reset. So what we're going to do is CPU memory equals null. We're going to have this C instruction register. So this is kind of annoying because if we want to reset, we don't want to leave, we don't want to have memory leak here. So what we're going to do is maybe create an initializer for the CPU. So we're going to say CPU init, and we're going to give it a pointer to a CPU, and we're going to do pretty much everything that we're going to do here, except down. In fact, when we reset the CPU, probably don't want to lose our memory. But what we want to do is we want to set our instruction to null. So now in our tests, instead of reset, we can do init CPU. So now we've initted our CPU, and if we ever do a reset, we can actually allocate memory as needed. And let's see, actually what we'll want to do is the instruction register. We'll want to go ahead and malloc for that anyway. So we'll create instruction, pointer to instruction, malloc size of instruction. Okay, so that will, when we initialize our CPU, we'll actually set this thing up just in case if we lose this, we'll reinitialize that. Okay, so that sets up our CPU. We should, let's see if that fixes it. So we'll do a build, init CPU, identifier not found. Let's see, oh yeah, we need to, let's see, test SIA, init CPU. Let's see, so we're missing init, oh, CPU init, that's what it is. CPU init, we just had the wrong name. So let's do a build. We've got a correct build, so then we can do our tests, and it looks like everything passed. So we actually had to allocate memory to our instruction register. So that seems to be pretty good. So running is 0, so that's very good. So running before was 1, and then when we set it to false, should be 0. So that looks like it's running pretty good. So now we have a CPU that when we call run, it'll set running to true. While it's still running, it will fetch and decode and execute an instruction. Then it will increment the program counter, and it will execute the instruction. So the first thing that we can do to do this is to actually test to see whether we can actually run a program. So this will be CPU init in our main function, and what we should do is we should create some memory. So let's create a byte memory, and what we're going to do here is we're actually going to write a program. So 01 is let's see, remember from our design document that 01, it sets register A to an immediate value, and then we're going to set register B to an immediate value. So we're going to do this. We're going to have a byte that we're going to set register A to an immediate value of, say, 3. Now let's see, I wonder how this will work, because this should actually be turned into multiple bytes. We may have to end up writing some more interesting stuff here. We'll just try it out. We're going to do OX02. This should be register B. We'll set that to 4, and then we'll do an add instruction, which ends up being, what is add? Add is 16 in hexadecimal. So we'll do that. That's our add instruction. And then we'll have a halt instruction, which is 2E. So let's do that, 2E. Now we have our memory set up. So now we have, let's see, let's take our CPU, and we'll set our memory to memory. So now we have memory, and then we can do run of our CPU, and then after we're done, we can print out register A should be 7 and is and then we'll have to convert this to int64t. Oops, there we go. I do not have high confidence that this will actually work. So what we're going to do is we're going to build that. So it built, oh, that was for tests. So let's actually do build.bat. Okay, cannot convert initializer list to byte star. Initializer contains too many elements in CPU 9. Yeah, that was a problem that I thought. So what we're going to try to do here is we're going to create a, let's actually create instructions. Oh, no, there's no easy way to actually set up our memory the way that we have our instructions set up right now. I mean, we could write this thing out byte by byte, but then we'd have to worry about the endianness of our machine. So I'm going to have to think about this, because until we have a assembler where we can put in some assembly code instructions and have it spit out the right binary, it's going to be a little bit annoying to actually write this binary by hand. So I'm going to take a look at that, but for right now we actually have quite a bit done. We have our main CPU thing. We still need to test our main CPU loop, but we have some more instructions in our opcode. Actually up here, we're setting in opcode, we're actually setting our registers A, B, and C with immediate values. What that means is that an immediate value is just a value that we're going to take from our program directly and put it into a register. So we've done that. We've actually written tests for that. That's some pretty good progress for this video. In next video, we're going to take a look at solving this problem of how to write programs and test them in our memory without having to worry. Well, we need just an easier way to do that, because we're eventually going to create an assembler for our machine, but that is a whole other project that we don't want to start on yet. So thank you for watching. Till next time.